Alright, so hey everyone, let's go ahead and finish off this hypothesis test so we could finally move on to some slightly more complex models that I think are a little bit more interesting and that they at least have. We'll start with just adding one predictor to our model next time. But for now, we were answering this question of whether there was evidence that the mean that the mean course evaluation score at the University of Texas Austin is different than a 4. So remember, the evaluation score was just on a scale from 1 to 5. We had done the prepare step, and so now for our check, we're going to first check the independence assumption. And so the description of the data actually didn't tell us how exactly the data was collected, but let's first assume that each case in the data set is actually from a different professor. If that's true, then I think we can say that independence holds, since each professor is providing us with new information. New information about evals, or evaluations. If, however, we assume that the same professor appears multiple times in the data set, because each professor is going to end up teaching multiple courses, then we might investigate a little bit more this independence assumption. We're going to write does not hold, but we would really need to look into this more. And the reason is that knowing a score for one course for a given professor, we'll say for Professor A, tells us something about his or her other courses. And so in that way, the courses are kind of connected, and they're connected by professor. For now, we're just going to assume that it holds and carry on with the rest of the test. So our sample size condition, to assess that, I'm going to go back and look at the histogram. I'm seeing that it's slightly left skewed, right? And so the slight left skewness doesn't really matter because we have a big sample size. So our sample size is bigger than 30, and we saw in that histogram that there's no extreme skewness or extreme outliers. All right, and so now for the calculate step, this should look pretty similar to something that we've already seen. So remember, for proportions, we found a z-stat as that. This structurally looks very, very similar, except now instead of using the z distribution to get a p-value, we're going to end up using the t distribution. And so for this particular example, let's first calculate the standard error. And so it's just the standard deviation divided by the square root of the sample size. So going back to our prepare step, we had already written down what those were. So that's nice and easy. Just plug in those numbers and you get our standard error. The t-stat, again, this is what I think is the easiest part of stats, and that's just the kind of calculation. Once you have all the numbers written down, we're just going to plug them into the appropriate equation. So if you do that calculation, so that's our sample mean minus what was our hypothesized mean if the null hypothesis is true, divided by the standard error. And now again, really similar to what we did for proportions, we're going to draw this t-distribution if the null hypothesis is true. And so remember, we always drew these distributions as if the null was true. We're going to mark our observed t-stat on this distribution. So it's somewhere like way out in the tail, and then shade both tails for our p-value. To get the exact shape of that, we would also need to know the degrees of freedom, which in this case are just 462. And so remember, the logic here is then that, oh, okay, I'm seeing if the null hypothesis is true, I would see t-stats that look like this. What we observed was like way off the graph. And so my conclusion logically from that is, well, if our observed t-stat was so unusual, then the null hypothesis might not really be true. And we're seeing that if we use StatKey to actually get the p-value, StatKey will tell you that the p-value is very close to 0. So we're just going to write it as close to 0 or maybe less than some really small number. And so our p-value is also telling us, like, wow, there's a lot of evidence for the alternative hypothesis, or there's a lot of evidence that the mean course evaluation rating at the school is different than 4. And so for a conclusion, we're again going to write it as 2 sentences. The first is we always want to make sure to include our point estimate in the conclusion. So we want to say we estimate the mean course evaluation rating at UT Austin to be 4.174 points. So that was our sample mean. After we write our point estimate, we want to say how much evidence we've got for the alternative hypothesis. And in this case, since our p-value is really tiny, we want to say something like, okay, there's strong or convincing evidence that, and then we just want to write what that alternative hypothesis was. So that the mean evaluation score is, we can either say different than, because that's how it was worded in the original alternative, or we could end up saying greater than, just to kind of match it with what we actually observed. Either way, since we included this point estimate, any reader is going to be able to realize that the reason that it's different than 4 points is because it's bigger. And then I just want to say at the end what my t-stat was and what my p-value was. So we're matching the structure of the conclusion to exactly what we did with proportions. Okay, and so the next time we'll start talking about exploring scatter plots and correlation, which will lead us into some regression models, where we might be interested in including some predictors for, say, course evaluation score. And so if you look back. So we've got these other variables. I might want to know, does age seem to be associated with course evaluation score? Or does attractiveness seem to be associated? And so those are the questions that we'll start to be able to answer once we move into regression.